Sachi, and we are reacting to Alien Biospheres Part 14, Mass Extinctions from Biblaridion. I still don't know how to say the name. Anyway, this is the second to last video that they're making for this series, I think. And I didn't decide to make this video until today.
The time has finally come. So be it. For hundreds of millions of years, the chemophytes, anthostomes, and polypods have held dominion over the biosphere, proliferating into millions of species and adapting to every environment across the globe. But now, after such a long era of success, a disaster is looming on the horizon that will change the face of life on this planet forever. To begin with, extinction is a natural and indeed essential component of evolution. The fundamental premise of natural selection is that individuals with more adaptive traits will survive and pass those traits on to the next generation, while those that are less well adapted will die out and their deleterious traits along with them. This pressure to stay ahead of extinction drives species to constantly innovate and diversify, and results in the extraordinary variety of forms we see across the biosphere. Amid the constantly changing conditions of the natural world, there's plenty of opportunity for species to lose out in the struggle to survive, and throughout the history of life there will always be a background rate of extinction, which is usually balanced out by a more or less equal rate of speciation. But occasionally, the extinction rate rises to the point of exceeding the speciation rate, resulting in what's known as a mass extinction, or, more generally, an extinction event. Under the most inclusive definition, there have been dozens of extinction events throughout the history of life on Earth, as will be the case on our alien planet as well. For the sake of simplicity and clarity, this series has only focused on the major clades and the broad-scale patterns of their diversification. Realistically, there will have been countless other clades that have come and gone alongside them, and between every branch of the tree of life will be innumerable offshoots that leave behind no descendants. So far, the planet has been through several minor extinction events, like the collapse of the rainforests and the spread of the brachyphyte steppe, the onset and ending of the Ice Age, and likely many other events that we haven't detailed. But once every 100 million years or so, an extinction event occurs that reshapes the entire biosphere beyond recognition. The most intense mass extinctions in the history of Earth are known as the Big Five, the most famous of which being the End Cretaceous or KPG extinction that wiped out the non-avian dinosaurs along with many other groups. But the most devastating was the End Permian extinction, also called the Great Dying, which killed off more than half of all family-level clades and as much as 90% of all species. With the exception of the End Cretaceous extinction, which is known to have been the result of a meteor impact, the exact causes behind these extinctions are still under study, but virtually all of them are associated with periods of increased volcanism that led to huge disruptions in climate. But no matter the trigger, the ultimate cause of all mass extinctions can be boiled down to sudden, inescapable worldwide change. Most climate shifts take place gradually over many millions of years, during which time beneficial mutations can accumulate to allow species to adapt to the changing conditions. But mass extinctions typically occur on the order of thousands of years, which simply isn't enough time for evolution to keep up, and so species just have to make do with what they've got. The first stage of the mass extinction on our alien planet will be set in motion by the movement of the continents. Ever since the eastern and western continents began heading back towards each other, they've also been steadily drifting southward, so that as they collide, they'll intrude into the Antarctic Circle, providing more land area for glaciers to form. On top of this, the collision will push up new mountain ranges and increase volcanic activity, which will release sulfurous gases and other particulates into the atmosphere to form thick clouds that increase the planet's albedo, reflecting more and more solar radiation and resulting in global cooling, plunging the world into a new ice age even more intense than the last one. Many of the animals that have thrived in the hothouse period of the last 50 million years may struggle to survive, But before anything has the chance to adapt to this colder world, the situation will rapidly reverse. Volcanoes also produce an enormous amount of carbon dioxide and other greenhouse gases, which, as the eruptions continue over the course of several 100,000 years, will cause global warming by which the planet's average temperature will rise to unprecedented levels. On Earth, the Great Dying saw average global temperatures increase by up to 10 degrees Celsius, brought on by a series of massive eruptions that caused a six-fold increase in atmospheric carbon dioxide over a period of about 10,000 years. Although it's worth noting that this isn't even close to the rate at which humans are currently putting CO2 into the atmosphere. This sudden switch from bitter cold to scorching heat will throw the climate into chaos, resulting in wild oscillations in weather patterns all across the planet. Worse still, such large-scale eruptions will cause flood basalt events, in which enormous tracts of the landscape are ravaged by lava flows. The Great Dying saw flood basalts cover an area of over 7 million square kilometers, resulting in the formation of the Siberian Traps. All of these factors will bring about destruction on a scale the planet has never seen, presenting a threat to the entire biosphere that only the hardiest of species will have a chance of surviving. In general, plants are more resistant to mass extinctions than animals are. Many extinction events in the history of Earth haven't significantly affected plant diversity, so the majority of chemophyte clades may survive in some shape or form. However, while plant diversity won't be severely affected, plant biomass will be hugely reduced, and the distribution of biomes and habitats will change dramatically. The shift in climate will lead to widespread drought, and the ash and aerosols in the atmosphere will block out the sun for months at a time, causing forests all across the planet to die back. The intense heat will ignite the withered remnants of these forests and spark huge wildfires, releasing yet more carbon dioxide. Though many plant clades may be diverse enough to make it through, some won't be able to cope with such huge changes to their habitat. The most significant factor affecting the likelihood of a species extinction is its degree of specialization, as the narrower the range of conditions the species is adapted for, the more sensitive it will be to any changes in those conditions. In this way, the inhabitants of the rainforests will be especially vulnerable, as the rainforest's sheer density of niches and its unchanging, accommodating climate engender specialization by their very nature. As the largest of all chemophytes, the altophytes are only able to achieve their enormous height thanks to the high levels of solar radiation and the perpetual rainfall of the tropics. But as weather patterns across the planet are disrupted, the constant precipitation that fuels the growth of the rainforests will cease, and without sufficient sunlight or water, the altophytes will be forced into extinction. These enormous trees serve as the foundation of the entire rainforest biome, and once they disappear, the countless species that depend on them will be in dire trouble. Many of the smaller rainforest plants are adapted for life in the darkness of the forest floor, and don't require as much water or nutrients to grow, but many of them will still be too specialized to tolerate such an extreme environmental upheaval. In particular, carnivorous plants are found almost exclusively in very wet habitats, as carnivorian plants is most often an adaptation to waterlogged, nutrient-poor soil. So as the tropics become more arid, the carnivorous harpactophytes won't have any suitable areas to grow, and so will be swiftly driven to extinction. For ground plants like the conophytes, the drier climate will not only make it harder for them to grow, but it will also affect the populations of scavengers and detritivores that they rely on for their deceptive pollination, inhibiting their reproduction as the jungle disappears, meaning they too will vanish from the forest floor. The situation will be equally bad for epiphytes, which rely on the enormous trees around them to lend them the support they need to gain access to light. Though the reptophytes, chromatophytes, and aphyllophytes may be widespread enough to survive as a whole, the rainforest species will be hit especially hard, as most of them have specialized to the point where they can't survive at ground level at all. With the decline of these plants, the intricate relationships they've evolved with the rainforest animals will be severed, leading to their demise as well. Many of the rainforest picopterans are only able to feed on a single species of chromatophyte, and in turn serve as their only means of pollination. So as one clade declines, the other will respond in kind, and although some particularly small and adaptable species might manage to survive elsewhere, the vast majority of picopteran diversity will be lost. Similarly, the phyllophorans have evolved to mimic the leaves of specific species of chromatophytes, and to feed on the individual species of nectarovores that the chromatophyte attracts. But depending on a suitable abundance of both of these clades makes their niches inherently precarious, meaning it will be virtually impossible for them to survive once the rainforest ecosystems collapse. But the rainforest animals depend on the plants around them for more than just food. Many arboreal species are so highly adapted for life in the canopy that they're completely incapable of coming down to ground level. Animals like the suspensorial harpactopods and the canopy-dwelling aspidons require a high density of vegetation for their locomotion and hunting strategies to be effective, and the tannibrachids are so specialized for brachiation that their legs have lost the ability to support their weight and have become virtually vestigial. With the death of the altophytes, obligately arboreal animals like these will be some of the first to die out. The dolichostracans are also predominantly arboreal, so the majority of them will die out as well, save for those few species that can locomote effectively at ground level. In particular, the phylactocanthids are so arboreal that they depend on the hoplopods to ferry them to new feeding areas. But as the groves of trees they thrive in become increasingly rare, their feeding and dispersal will become much more difficult, until they too ultimately succumb. And without their phylactocantid symbiotes, the hoplopods will be robbed of their means of defense, and with food becoming scarcer all the time, they too will eventually disappear. Not long after the specialists are wiped out, the shortage of food will begin to affect other groups. Another factor strongly correlated with extinction risk is body size, as larger animals tend to require a greater amount of resources, which become much rarer during mass extinctions. Plus, large-bodied clades tend to have lower species richness and smaller populations, as well as longer growth periods and slower reproduction, making it harder for them to stay ahead of rising mortality rates. Once the climate begins shifting, it won't be long before megafauna start dying out. Even before the mass extinction, the titanopods haven't been faring well. The majority of species outside the tropics were killed off by the last ice age, and the surviving species have been losing out in competition with the allobrachids. For what few species remain after the interchange, the mass extinction will be the final nail in the coffin. But their allobrachid competitors won't fare much better. The phylacrobrachids and teleobrachids have evolved sizes comparable to the titanopods, making their chances of survival similarly remote. Even the smaller allobrachids won't. In what's sometimes called the Lilliput effect, mass extinctions often cause a worldwide reduction in body size across virtually all animal clades, which, in mass extinctions on the scale of the Big Five, means that any animal larger than about 10 to 15 kilograms is liable to be wiped out. As the lush plains are replaced by barren wastelands, the herds of basal neobrachids, ceratobrachids, corythobrachids, and any other remaining thylacopods will disappear one by one. Their camptopod relatives will follow the same fate, having already taken a substantial hit to their diversity when the allobrachids crossed into the east, and now finally being finished off once and for all. The situation will be no better for all the varieties of herbivores. Most of the prenobrachids and the basal megalobrachids were outcompeted by other megafaunal clades long ago, and any species that are still around will be doomed. The disappearance of large prey will propagate through the food chain and take its toll on the predators. The large onocodonts have been the most successful clade of apex predators since the invasion of land, but as their hunting grounds are depleted, their supremacy will at last be brought to an end. Although the terrestrial Deinognathans have more generalist diets than the onocodonts, they'll still struggle to find enough food to maintain their large size, and even the smaller opportunistic groups like the Maliognathans and Lestignathans won't be able to eke out a living in the desolated remains of their former habitats. The semi-aquatic dinignathan's will also begin to disappear as freshwater habitats dry out in the searing heat. The macropredatory trachognathans won't be able to survive without an abundance of big game, and most of the freshwater dolichognathans will also perish as their habitat diminishes. Even flying species won't be able to escape the destruction. Although birds as a whole survived the end Cretaceous extinction, representing the only clade of dinosaurs to make it to the present day, many of the most successful groups of birds during the Cretaceous didn't survive the meteor impact, and the pterosaurs were wiped out altogether. The theropterans and other large pleropterans are too big and specialized to survive, while the magnopterans have already been on the decline from competition from the pleropterans for tens of millions of years, so they won't have the necessary diversity to persist, and the sphenopterans' speed and pursuit hunting adaptations will be of no use in the absence of prey. But the devastation won't be confined to the mainland. As we've touched on in previous episodes, islands are much more vulnerable to extinction than continents, as they can't support the same level of resources and diversity as larger land masses. This same effect can be seen in habitat fragmentation, in which large areas of landscape are subdivided into patches between which dispersal is inhibited, which makes each individual fragment more vulnerable to biodiversity loss. Most of the islands in the Pyrenesian archipelago are only a few tens of kilometers across, which constrains the population sizes of their native species and makes them more sensitive to environmental disturbance. So the majority of Pyrenesian fauna will die out shortly after the climate begins changing. And if that weren't enough to seal their fate, the volcanic hotspot that fuels the formation of the archipelago won't remain active forever, and as the islands drift over it, they'll gradually be eroded by wave action until they crumble into the sea, and all of Pyrenesia's unique indigenous clades will disappear with them. The island of Crescentia will suffer an even worse fate, as it will have the misfortune of being right at the center of the continental convergence, first freezing over as it nears the South Pole and the cooling period begins, then scourged by tides of lava once the eruptions ensue. What few notiforms and xenodonts survived the Ice Age and the arrival of the Eryatheres will be promptly snuffed out, and even the Eryatheres themselves won't be able to survive as the island is made completely uninhabitable by the ongoing volcanism. The mass extinction will present an entirely different range of threats to oceanic ecosystems. As the ash clouds darken the sky, the phytoplankton that form the basis of the marine food webs will have a harder time photosynthesizing, depriving the swarms of tachypods, anthostome larvae and other zooplankton of their food source, and the once prolific swarms of tiny organisms will vanish from the surface waters. Additionally, the rising levels of CO2 will react with seawater to form carbonic acid, increasing the pH of the oceans and making it harder for species with mineralized exoskeletons to form their shells. This ocean acidification was a major factor that led to the marine invertebrates suffering the heaviest losses during the Great Dying, with many clades losing over 90% of their diversity. Anthropogenic climate change is beginning to cause similar effects, such as coral bleaching and the reduction of calcification of many oceanic organisms. Most of the marine anthostomes have calcareous shells, and the reefs formed by the sessile species in coastal waters are some of the richest of all marine habitats, and their death will cause a catastrophic decrease in ocean productivity and cause entire food webs to collapse. On top of this, the changing climate will drastically alter the ocean currents, causing huge disturbances in the distribution of oxygen and nutrients. This is made worse by the fact that as water becomes warmer, its levels of dissolved oxygen decrease, which, along with the changes in ocean chemistry and productivity, will result in an anoxic event, turning large expanses of the seas into dead zones, areas where oxygen levels are too low for any marine animals to survive. Just as on land, the biggest and most specialized marine species will be the most vulnerable. The largest animals in the sea, and indeed anywhere on the whole planet, are the thalattotheres, including the filter-feeding isopterygians and the predatory anisopterygians, many of which exceed 10 meters in length. At such a huge size, even the slightest change in the distribution of resources presents a serious risk, making their extinction inevitable. Even the smaller semi-aquatic animals, like the actothias and diptopterids, don't have comparable levels of diversity to fully marine groups, and so won't be widespread enough to outpace their rising death toll. Many fully marine clades, like the acanthopods, coleopods, and tentaclostomes, will also take heavy losses. Particularly, large filter feeders like the tylopods depend on high concentrations of plankton and oxygen, and apex predators like the temnopods can't survive without sufficient quantities of large prey. But the marine clades won't be the only ones affected by the change in ocean chemistry. At the bottom of the sea are large deposits of methane clathrate, a form of ice consisting of bubbles of methane held within a lattice of water molecules. These clathrates are only stable under high pressures and low temperatures, so as the sea warms up, the clathrates will dissolve and release the methane from the ocean depths into the atmosphere, a mechanism known as the clathrate gun. As methane is a far more potent greenhouse gas than carbon dioxide, this will result in an even sharper rise in global temperatures, and create a feedback loop by which they climb higher and higher. For thousands of years, the entire planet will be smothered by the oppressive heat and clouds of ash, as lava flows lay waste to vast swathes of landscape, and once fertile habitats are reduced to baking deserts, and species die out at a higher rate than any other time in the planet's history. It will be millions of years before conditions become tolerable again, but even after the eruptions end and the planet begins to heal, some of the survivors may later succumb to extinction debt, having lost so much of their former diversity, abundance, or habitat that they'll be unable to recover, and will be doomed to die out at some point after the extinction event itself has ended. Although the basal platodonts are by and large very adaptable animals, many of the older varieties won't be able to deal with the massive change in conditions after the extinction. The copatarsons may be among those that lose out, as they never achieved a notable degree of diversity, nor did they spread much beyond the coastal swamps they first evolved in, making it harder for them to keep up with the constantly shifting climate. The echinostracans' main advantage is their spiked shell that makes them virtually immune to attack, but even if they survive the extinction, their signature adaptation won't be of any use when all the predators are dead, leaving them to be outcompeted by smaller, more adaptable plecostracans that can survive on less food. Over the enormous stretches of time that evolution operates, even clades that were once very successful and widespread may ultimately dwindle and die out. The trilobites were some of the most successful and abundant animals in the history of life on Earth, but after losing the vast majority of their diversity in the late Devonian extinction, they were never able to reclaim their former success before they were finished off by the Great Dying. And the multituberculates were the most diverse clade of mammals for over 130 million years, but despite surviving the end Cretaceous extinction, they ended up declining and dying out shortly afterward. Even groups like sharks and crocodiles, which have famously been around for hundreds of millions of years and lived through many extinction events, have still undergone significant losses in diversity. Roughly half of all crocodilians died out during the end Cretaceous extinction, and about 70% of all shark species disappeared in an extinction event about 19 million years ago. The basal dromaeopods were some of the first terrestrial predators to evolve, but since then they've been losing out against other predatory clades, and even if they manage to endure the mass extinction, they won't have enough of a competitive advantage to re-establish themselves. The leptopods have been some of the most successful herbivores in the planet's history, but with the death of the dominant groups like the allobrachids and the camptopods, the leptopods will have had their moment in the spotlight, and as new herbivores evolve, most of the remaining species will follow their larger cousins into extinction. At one time, the metaxopods were successful enough to invade the land and give rise to the osteophostomes, but since then they haven't been able to compete effectively with their osteopod descendants on land, nor with the acanthopods in the water, and what narrow range of niches they'll have managed to occupy will be compromised by the mass extinction, even to the point of wiping them out completely. The only animals that stand a chance of surviving are those that are small, generalist, and resilient enough to cope with extremely rapid and drastic changes to their environment. though there'll be considerable turnover in many marine ecosystems. The tachypods and other constituents of the plankton are so abundant and have such a high fecundity that some tiny fraction of their diversity will survive, persisting in the few patches of sea that retain enough oxygen and nutrients, and rapidly multiplying to refill the empty oceans once conditions become favorable again. The smallest members of the major clades of acanthopods will also survive, as will the coleopods and the lithostracan tentaclostomes within the relative shelter of the ocean depths. Being limited by their lack of internal support to only a few kilograms at the most, the majority of the lophostomes will be within the range of body size necessary to avoid extinction. In particular, the malacoforms are so small and diverse that they may make it through virtually unscathed, much like how insects have been largely unaffected by most extinction events in the history of Earth. The Xerostracans can make use of their estivation to sit out periods of intense drought and famine, which they may make use of to become one of the most successful diplostome clades during the extinction event. Though the larger opisthophorans, like the magnopterans and sphenopterans, will be wiped out, many of the leptopterans have remained small enough to make it through. Although the reduction of chromatophyte abundance will pose a danger for nectarovores, a tiny percentage of picopterans will be small enough and reproduce quickly enough to survive on the decreased food supply, just as how the lepidopterans survived the end Cretaceous extinction, while most pipiodonts are opportunistic enough to get by on malacoforms, seeds, and other meager scraps of food. As most of the flightless elastospondylus are arboreal, the worldwide deforestation will claim a large chunk of their diversity, but some of the basal species may still be able to find small prey at ground level and within the isolated pockets of woodland that remain. The trophophorans may survive by virtue of their infrared sensing, by which they can find and hunt prey more easily than many other elastospondylus, while the survival of the dinoglossids won't be as contingent on the availability of food as it will be on the abundance of their scandapod host species. Fortunately for them, the scandapods are some of the smallest and most diverse of all platodonts, and while they'll certainly undergo a reduction in their diversity, the clade as a whole will still survive. The Pleuropterans were able to achieve sufficient diversity prior to the extinction event, such that, although the Theropterans and many of the larger, older, and less competitive Pleuropterans will be killed off, a handful of Platypteran species will be small and successful enough to survive. The amblypods were lucky enough to be adapted to arid habitats before the mass extinction, which will make them the only clade of leptopods to survive, consigning these once prolific herbivores to only a few small species wandering the deserts and scrublands. But of all the polypod clades, the Seniscians will have suffered some of the heaviest casualties. From the very beginning of their history, they've been specialized for attaining large sizes, developing robust, weight-bearing skeletons and becoming some of the first terrestrial animals to move into megafaunal niches. But in the long run, these very same traits will be their undoing. After the marine forms are wiped out and the terrestrial species are all but annihilated, almost the entire Seniscian lineage will be gone. But sometimes, whether a clade lives or dies during a mass extinction comes down to sheer luck. Along the coasts of Septentria, the climate may remain hospitable enough for a few patches of wetland to be preserved, and within their waterways, some scattered populations of the Hybignathans may be fortunate enough to be spared, living on the few diplocerids and other freshwater acanthopods that still dwell on the shrunken remnants of the once expansive river systems. And even then, only one genus will survive, clinging on in the Septentrian swamps as the very last of the Seniscians, and a bizarre relict of a bygone era, just as how the Tuatara lives on in New Zealand as the only remaining species of the once widespread Rhynchocephalians. But not all of the surviving clades will emerge from the extinction event in such a sorry state. For some clades, the destruction will bring opportunity. Whether they're wiped out by the mass extinction or simply lose out in competition with their more adaptable relatives, the older clades of Eurychirids will be forced into decline, as will the more specialized groups among them like the Apatochirids, who depend on dense populations of their host species to implement their brood parasitism. But many of the other Acrochirids, along with the Oryctochirids and some of the basal Ramphidonts, have a suite of characteristics that will make them some of the most successful animals during the extinction. extinction. Their small size means they can survive on very little food, and their diets are broad enough to subsist on whatever they can unearth from the barren soil. Their endothermy lets them maintain constant activity and makes them less sensitive to fluctuations in climate, and they can avoid the worst of the perilous conditions on the surface within the shelter of their burrows. They have very high reproductive rates, and their extensive brood care and social systems ensure that a high proportion of their young make it to adulthood. With this array of adaptations, these little creatures are poised to not only survive the extinction, but also to act as pioneer species, which in the context of mass extinctions are sometimes called disaster taxa, being some of the first animals to recover and thrive in the post-extinction world. But they won't be alone. All that will remain of the dromaeopods after the extinction will be the allodonts, most older clades of which will also perish soon afterward in competition with other groups. But if any of them survive, the xenopsids will certainly be among them. With their unique feeding arrangement, these small, tenacious mesocarnivores can feed on anything from rotting meat to plant tubers, and their facultative endothermy lets them tolerate variable climates and slow their metabolism to conserve energy during times of food shortage, not to mention the increased survival rates afforded by their social behaviors and cooperative breeding, all traits that will let them establish themselves as a dominant clade after the mass extinction. Even as these surviving groups begin to repopulate, the scars left by the mass extinction will be all too clear. Whereas before the extinction event, there was a more or less seamless spectrum of forms across the tree of life. In the aftermath, so many branches will have been removed that the survivors will appear to be grouped into distinct clusters that share key traits in common. This effect can be seen on Earth in the fact that clades have historically been described in terms of classes, such as how vertebrates have been traditionally sorted into mammals, birds, reptiles, amphibians, and fish. However, these groups only appear distinct from each other because the intermediate forms have gone extinct, and if we take these into account, it becomes much more difficult to distinguish where one group ends and another begins. In reality, these classes are defined almost arbitrarily, and often don't represent valid cladistic divisions. Of the osteopods that survive the extinction event, two of the most distinctive groups will be the xenopsids and the ramphidonts, which, since their Peliscian ancestors diverged from each other over 200 million years ago, have each inherited a unique assortment of distinguishing features. The ramphidonts are characterized by their beak-like mandibles, enlarged anterior eyes with external dilating membranes, antennae-like pedipalps with tympanic hearing organs within their proximal segment, digited forelimbs, endothermic metabolism, and altricial grub-like offspring, while the xenopsid signature traits include their serrated pedipalps with apical hearing organs, their binocular-like lateral eyes that bear sclerotic rings, coat of pectinate setae, internalized gonopods, and facultative endothermy. Both of these groups will be immediately distinguishable from all of the remaining Peliscians, while the few hibignathans that live on will form a peculiar outlier as a sister clade to all other osteopods. But now that the mass extinction has passed, these surviving clades will have the whole world to themselves, and with so little competition, they'll be free to establish an entirely new dynasty. We've mentioned before that when species find their way to uncolonized habitats, like islands, they rapidly undergo an adaptive radiation to take advantage of all the empty niches. Mass extinctions have the effect of turning the entire planet into an uncolonized habitat, triggering an adaptive radiation on a global scale. This concept is termed punctuated equilibrium, whereby long stretches of evolutionary stasis are interrupted by spurts of rapid diversification, usually as a response to sudden environmental disturbances like mass extinctions. Additionally, the reduction of competition means that species can afford to experiment with new designs and survival strategies, and as a result, the period immediately following the mass extinction is likely to produce some of the strangest clades in the planet's history, much like the explosion of bizarre groups that appeared during the Triassic period following the Great Dying. The first stage of recovery will occur over several million years as plants and eroding mountains start to slowly absorb the excess carbon dioxide and return the atmosphere to equilibrium. Once the climate stabilizes, the process of secondary succession can take place and new ecosystems can be established. The chemophytes will slowly begin regaining ground as the landscape once again becomes suitable for the growth of forests. However, whereas beforehand the xylophytes were the dominant clade of trees, replaced them.
Many mass extinctions on Earth coincide with significant changes in vegetation, such as how the death of the lepidodendron.
The landscape once again becomes suitable for the growth of forests. However, whereas beforehand the xylophytes were the dominant clade of trees, the mass extinction will provide other plants with the opportunity to replace them. Many mass extinctions on Earth coincide with significant changes in vegetation, such as how the death of the lepidodendrons and the other lycopsids during the Carboniferous rainforest collapse led to the rise of the conifer forests, and the end Cretaceous extinction saw the flowering plants replace the gymnosperms as the dominant form of tree in tropical and temperate latitudes. Up until now, the zygophytes have remained relatively small ground plants, but as the trees around them vanish, they may be able to recover much faster than the xylophytes and evolve into a new form of tree, adapting their ramets into trunks and branches bearing colorful inflorescences composed of their hair-like gametangial filaments. The reef-like jungles that these colonial trees form will constitute an entirely new type of habitat, while the forests of xylophytes will only occur further towards the poles in colder and more arid regions. These new trees, which we'll call zygodendrons, will provide innumerable niches for a myriad of arboreal species. As some of the few forest-dwelling animals to make it through the extinction, the surviving scandipods will begin to replace the extinct varieties of arboreal platodonts. Whereas the early scandipods' tiny size let them move along narrow branches, the new, larger forms will need to adopt other methods of arboreal locomotion. In one group, the limbs will elongate to help reach between gaps, and their feet will develop flexible joints and hooked claws to let them grip to vertical surfaces, leading to a clade of scansorial and suspensorial forms that we'll call the fulcoscalids. Some fulcoscalids will be small fruit and seed eaters that dwell on the zygodendron's gametangial filaments, while others will be meter-long predators that snatch up smaller scandipods scuttling along the branches below them. Meanwhile, a separate lineage will evolve in the opposite direction, developing longer, more gracile bodies to let them maintain balance on narrow footholds and to squeeze through dense vegetation, and short, strong legs to let them cling to the underside of branches. Both the fulcoscalids and this new clade, which we'll call the brachyscalids, will represent the vast majority of scandipod diversity in the new era, both radiating into thousands of new species. But at ground level, the ramphidonts will undergo a diversification event of their own, modifying their ancestral design into a plethora of new forms. One curious adaptation that's occurred in several vertebrate clades is limblessness, the most obvious example being snakes, but also seen in other reptiles like the legless lizards and amphisbaenians, and even in amphibians like the caecilians. In virtually all of these groups, limblessness seems to have evolved as the result of a burrowing lifestyle. After all, fossoriality is associated with the reduction of any external structures that might get in the way while burrowing, including the limbs if they don't play a significant role in digging. The fossorial ramphidonts are already born without any solidified bones in their limbs, making them of little use in walking, so the grub's primary means of locomotion will be writhing or squirming, wriggling their bodies from side to side. If this proves to be a more efficient way of moving through loose soil, then some species may undergo neoteny, never developing limb bones even in their adult form and ultimately losing any vestiges of legs, retaining only their front claws that still serve in digging and handling food. As most species will spend the majority of their lives underground, the large eyes and acute vision of their ancestors will diminish, some species losing one or more pairs of eyes and some even being completely blind. There will be many hundreds of species of these serpentine ramphidonts, which we'll call apodomorphs, ranging in size from only a few centimeters to over a meter, found everywhere from the leaf litter of dense forests to the scorching sands of subtropical deserts. While the apodomorphs and many other ramphidonts will remain largely fossorial, the absence of any competition will coax many ramphidonts out of their burrows to exploit ground-level niches. While all ramphidonts have a light covering of setae, fossorial animals tend to have short or sparse fur to keep their bodies sleek, and larger animals can simply rely on gigantothermy for warmth. But the smaller species that move above ground may evolve a thicker coat of fur to make their thermoregulation more efficient. Additionally, the joints where their mouthparts attach to their skulls will evolve a unique structure that allows the independent movement of the left and right mandibles, a similar mechanism to the chelicerae of sun spiders. This will let them chew and process a wide variety of food sources, giving rise to an extremely successful radiation of generalists that we'll call the dystrophiognathans. In one branch of dystrophiognathans that remains small opportunists, their pedipalps will become long whip-like structures riddled with scent and taste receptors, with which they can probe through dirt, leaf litter, and other debris to pick out the tiniest scraps of food. The posterior portion of their abdomen will enlarge to house an expanded reproductive system, which, along with their tiny size and adaptable diet, will allow these generalists, which we'll call flagelliferans, to spread into virtually every habitat on the supercontinent and become some of the most prolific of all ramphidonts. In other dystrophiognathans that reach larger sizes, the huge claws of their fossorial ancestors will no longer be of any use in digging burrows, but one clade may instead use them to unearth subterranean food sources. From this lineage will come predators that break into the nests of oryctochirids, apodomorphs, and other fossorial prey, plucking them from their burrows with long serrated mandibles, as well as herbivorous species that dig up roots and plant tubers, and even forms that specialize for tearing open logs and tree trunks to expose malacoforms and other small prey beneath their cuticles. The broad spade-like claws that all of these forms share in common will earn them the name hadronychids. Another lineage of dystrophiognathans will evolve into small, adaptable predators and scavengers. These forms will develop pincer-like mandibles that terminate in narrow points to nip at and cut through soft meat, while also bearing ridged serrations to let them gnaw through tougher foods like bones, shells, and plant matter in times of scarcity. This clade, which we'll call dryptognathans, will fill the niches of mesocarnivores, scavengers, and small predators across much of the planet. As the dystrophiognathans proliferate, a separate branch of acrochirids will specialize for the roles of dedicated herbivores. One of the signature adaptations that distinguishes the acrochirids from other ramphidonts is their cecum that allows them to store and predigest food. While this first evolved as a way for them to process plant matter before regurgitating it for their grubs, it will also allow the herbivorous species to avert the contents of the cecum back into the foregut, in a similar way to how ruminants regurgitate and chew cud. In one lineage, the cecum will significantly expand, effectively becoming an extra chamber of the foregut where fermentation can occur prior to digestion. Again, however, it will take some time for the grubs of these species to develop such powerful, complex guts, making them less able to feed on vegetation than the adults. In some species, the juveniles will simply rely on their parents to provide them with regurgitated food that they can still digest, while in others this may result in ontogenetic niche shift, a phenomenon in which a species occupies different niches at different stages of its life cycle, which eliminates the risk of the juveniles being outcompeted by the adults. Therefore, while the adults will be more or less exclusively follivorous, the juveniles of most species will be much more generalist, feeding on fruit, seeds, or even subsisting on meat if need be. Another common adaptation among herbivores is for their jawbone to evolve an offset that allows the upper and lower teeth to all come into contact at once, improving their ability to grind down vegetation, which these forms may emulate by evolving a distinct right angle between the bones of their lower mandibles, allowing the flattened interior edges of the teeth to press together like a wrench, giving this line of acrochirids, which we'll call proseciforms, the most efficient plant-eating mechanism of any osteopod, and let them dominate the herbivorous niches in virtually every habitat. Some of these proseciforms will adapt for speed and cursoriality, not only evolving narrow unguligrade feet and elongated flexible spines, but also undergoing another instance of centaurism, becoming the first osteopods to run on only their hind two pairs of legs, with both the first and second pairs held off the ground. This radical innovation will reduce the energy required for running, giving them some of the highest locomotive efficiency of any clade yet to evolve. Some will only exhibit facultative centaurism, still keeping 6 legs on the ground when resting, while in others the front legs will effectively serve as a second pair of feeding arms. These swift quadrupeds, which we'll call oligopods, will branch off from the other proseciforms early on in their history, and will range from meter-long, lightly built grazers that forage within the groves of zygodendrons to large browsers that use their freed-up front legs to pull down tree branches. A separate clade of proseciforms will sacrifice speed to become lumbering megafauna, evolving enormous foreguts and multi-chambered stomachs, robust grinding mandibles to continuously harvest brachyphytes, and powerful muscles in their back anchored to bony crests to support their massive cephalothorax. As they don't need to be selective in their feeding, the antennae on their pedipalps will become reduced to nearly vestigial structures so as to not get in the way of the rake-like forelimbs that continuously sweep through the brachyphytes and pass food into the mouth. These gigantic beasts, which we'll call megantroforms, will be the largest grazing herbivores since the titanopods. In the scramble to fill all the empty niches after the mass extinction, some acrochirids may even be able to move into arboreal niches. In making this transition, one clade will not only develop long, flexible limbs for climbing and maneuvering through the tangled canopy of the zygodendron forests, but also a special foot structure with wide pads to give them strong purchase on precarious footholds and to adhere to near-vertical surfaces, as well as a tail-like dorsiventrally flattened posterior abdomen, which, along with the gonopods, will form a partially prehensile appendage to assist in maintaining balance and clinging to branches. These adaptable creatures, which we'll call hylotheres, will form a sister clade to the dystrophiognathans and proseciforms, and will serve as the precursors of another major radiation of acrochirids, one that will comprise thousands of species and be found in forests all across the supercontinent. As they diversify, different clades of hylotheres will adapt to cope with the numerous food sources available in the canopy. Many of the smaller hylotheres will have narrow tweezer-like mouthparts to probe for seeds, nectar, and malacoforms within the zygodendron's carpet of gametangial filaments, while larger species will adapt to feed on fruit, foliage, and other plant tissues. One group will even adapt for xylophagy, or wood-eating, a very rare feeding behavior among large animals, as wood is extremely nutrient-poor and difficult to digest. But in evolution, the pressure to avoid competition will always ensure that no niche goes unfilled. Therefore, the zygodendron forests will see the evolution of a clade of xylophagous hylotheres with vertically opposed chisel-like mandibles to gnaw through wood and other tough vegetation, and complex gut.
I'm back from doing something.
Guts filled with symbiotic microbes to help them extract as much nutrition from their food as possible. Their low-energy diet will make them slow and deliberate climbers, but they'll still find safety within the nests and burrows they chew into the dense labyrinth of branches as they feed. We'll call this clade the pelicodonts. But although the hylotheres will be ancestrally arboreal, over millions of years, as the distribution of forests changes and new habitats open up, the opportunity may eventually come for some clades to return to the ground. One group that makes this transition will evolve to walk on the knuckles of their front legs, helping to prevent their hooked claws from wearing down so they can assist the forelimbs in reaching for food. Though the early members of this clade will be mid-sized forest dwellers that pluck fruit from low branches, some may move out into more open habitats where, without the constraints of dense vegetation, they'll be free to grow into huge megafaunal browsers, the largest of which will rival even the megantroforms in size. These hulking creatures, which we'll call thaumatotheres, will comb the periphery of thick jungles and gallery forests, gorging on vegetation far out of reach of any other herbivore. With the return of megafaunal herbivores, it won't be long before predatory clades evolve to hunt them. The xenopsids have a head start over the ramphidonts in filling the niches of predators, as they already had a number of predatory adaptations before the extinction. In particular, the stenopsid's mouthparts, where the mandibles are concealed within a lip-like sheath and the pedipalps positioned further forward to more easily close over prey, enables them to make more precise and powerful bites than other xenopsids, making them somewhat pre-adapted for the niches of specialist predators. Soon after the mass extinction, one group of stenopsids will evolve to incorporate their forearms into their feeding structure, turning them into raptorial weaponry to latch onto prey and pull it within reach of the dagger-like pedipalps. From this clade, which we'll call the Peleropsids, will come a variety of predatory groups, including fast, step-dwelling pursuit hunters, agile semi-arboreal forms, and more heavily built ambush hunters. But one group in particular will develop the size and weaponry to become the first group of megafaunal hypercarnivores since the mass extinction. In these species, the raptorial forelimbs will become more robust and compact to allow them to restrain large prey like the oligopods, megantroforms, and thaumatotheres. As is befitting their status as some of the largest predators of the new era, we'll call these macropredators anaxotheres. The return of the predators will put pressure on their prey to evolve ways of defending themselves. Animals like the megantroforms and thaumatotheres can rely on their size alone for defense, but smaller animals like the diplostomes will resort to more innovative tactics. In one group of desmostricans, the excretory glands on their flanks will evolve to produce toxins, but instead of injecting venom through stingers like the pronacanthids, they'll instead adapt these glands into nozzles that fire the toxins in a chemical spray. This form of projectile weaponry is fairly rare, but can be seen in animals like bombardier beetles, velvet worms, and whip scorpions. In many species, the spray will consist of a noxious, foul-smelling liquid that repels potential attackers, while other species will produce strands of sticky, web-like slime that can entangle and entrap malacoforms and other small prey. To complement this weaponry, they'll also evolve aposematic coloration to make sure that predators know to avoid them. Due to their distinctive defenses, we'll call them mixobolids. Not all the xenopsids will be predators. Just as with the ramphidonts, the xenopsids will undergo an explosion of diversity and fill a wide variety of niches. In one group, the second claw on their forelimbs will elongate into a forward-angled spur against which the terminal claw can close, turning the distal portion of the limb into a structure similar to the chelae of many arthropods. These chelae will give them a much more precise means of manipulation, letting them selectively pluck up seeds, malacoforms, or other small morsels of food. We'll give this lineage the fitting name, calaferans. Although most calaferans will be small opportunists with narrow, pointed chelae, one clade will adapt for handling larger items like fruit, eggs, and even small prey like diplostomes, and so their chelae will evolve into robust, crushing claws to let them break apart their food before passing it into the mouth. These strengthened chelae will also serve as formidable weapons to fend off predators and compete with rivals for access to mates. These tenacious generalists, which we'll call pachycalaferans, will include some of the largest calaferans, found everywhere from zygodendron forests to arid steppe and scrubland, traveling in family groups in search of anything edible. The calaferans' chelae will help them become some of the most successful xenopsids, but one group of stenopsids will see an equally bizarre anatomical development. The bones at the base of the skull will develop tusk-like extensions that jut forward to form a larger surface for the pedipalps to grip against, similar to the head ornamentation of the extinct hell ants on Earth. These structures, which we'll coin the term exognaths to describe, will allow them to more easily bite down onto and grip food items, and from the forerunners of this new clade, which we'll call the ceratodonts, will arise a myriad of groups that each adapt these exognaths to suit different purposes. One clade may evolve to chase down small, fast-moving prey, using their exognaths to assist in snatching up and restraining their quarry. These forms will adapt for speed and maneuverability, evolving not only long, gracile bodies and powerful running legs, but also undergoing yet another instance of centaurism, the forelimbs tucking under the body to not get in the way when running, making these predators, which we'll call elaphrodonts, some of the fastest and most agile of all xenopsids. One clade of elaphrodonts will adapt their pedipalps and exognaths into pointed scissor-like structures, specialized not for grabbing but for impaling and skewering prey, and for delivering snapping bites to slice open lethal wounds. With this vicious armament, this clade, which we'll call the spathodonts, will become very diverse and successful predators, ranging from half-meter-long forest dwellers with long, supple bodies to maneuver through complex terrain in explosive pursuit of their prey, to 3-meter-long ambush predators that erupt from the undergrowth to dispatch their targets in a series of lightning-fast jabs. While the spathodonts will typically hunt relatively small prey, another line of elaphrodonts may make use of their speed, agility, and weaponry to go after megafaunal prey. In these larger forms, the exognaths will grow upward into knife-like points that interlock with the pedipalps in such a way that both are continuously sharpened as they shear against each other, like the carnassial teeth of many mammalian predators. As they adapt for hunting large prey like the oligopods, megantroforms, and thaumatotheres, they'll be brought into competition with the anaxotheres, which by this point will already be well-established macropredators. However, the speed and locomotive efficiency provided by their centaurism will let them compete effectively for the niches of pursuit hunters, while the anaxotheres will primarily rely on ambush tactics. We'll call these new hypercarnivores the xerodonts, but not all ceratodonts will specialize for predation. The increased ability to exert downward force provided by the exognaths will let them deal with food items too tough for most other animals, prompting some species to specialize for durophagy. In one group, the pedipalps will become more robust and heavily muscled, with huge rounded teeth to compress down against the exognaths like a vice, which scavenging species may use to crack open the bones of carcasses, while herbivorous forms may use them to crunch through tough woody plant tissues. We'll call them cophodonts. In yet other ceratodonts, the exognaths may serve as multi-purpose tools for manipulation, display, or defense. In one predominantly herbivorous group, the exognaths will become horn or antler-like structures to help them dig through the topsoil in search of roots, tubers, and other plant matter. These horns are also likely to be co-opted into weapons and ornamentation in fighting for and attracting mates, even to the point of undergoing fishery and runaway in some species, with males bearing horns so large and unwieldy that they encumber their movement and their ability to feed. Although some ceratodonts such as these, which we'll call aratrodonts, will develop herbivorous tendencies, it will be a separate branch of synopsids that comes to fill the niches of large herbivores. While large ramphidonts, like the megantroforms and thaumatotheres, will come to fill most of the niches of megafaunal herbivores, the synopsid's coat of pectinate setae lets them more easily adapt to colder climates than the ramphidonts. So one group of synopsids may manage to fill the roles of large browsers in the seasonal forests and tundra towards the south of the supercontinent. As some of the relatively few fully herbivorous synopsids, their enlarged lateral eyes, which in most synopsids face forward to grant them binocular vision, may instead angle sideways to give them a full view of their surroundings to look out for danger, giving them a distinct hammerhead condition. From this lineage, which we'll call the teleopsids, will come large folivores that wander through the xylophyte and notophyte forests, as well as stocky, tundra-dwelling grazers and smaller forms that dwell atop mountain crags or rocky plateaus. But as all these various groups recolonize the land, there will also be plenty of empty niches in freshwater and marine habitats, which will incentivize some groups to develop semi-aquatic lifestyles, just as how many secondarily aquatic groups on Earth first evolved shortly after mass extinctions. One group of basal synopsids will begin the transition to aquatic life by wading into the shallows of rivers and lakes to hunt acanthopods. In so doing, the claws on their forelimbs will adapt into a line of needle-like points, reminiscent of the teeth of many piscivores on Earth, an ideal shape for grabbing onto slippery aquatic prey. Their spiracles will move onto their back to let them breathe while the majority of their body is submerged. The dense covering of pectinate fur common to all synopsids will create excess drag when swimming, so many species will become hairless, as many aquatic mammals have done on Earth. These synopsids, which we'll call anchistrabrachids, will be commonly found along riverbanks and lakesides, standing motionless with their forelimbs splayed out and snatching up any acanthopod that comes within reach. Some of the ramphidonts will also have semi-aquatic representatives. In the river basins of the tropical forests, one clade of hylotheres may evolve to traverse the flooded waterways by adapting the pads on their feet into broad flippers. However, the developmental changes that the ramphidonts' grubs undergo as they mature may influence how they make the transition to semi-aquatic life. In some species, the juveniles will be exclusively terrestrial, gradually becoming more adapted for swimming as they age, whereas other species will live in the water from birth. In the latter species, the grubs won't develop the leg bones necessary for limb-driven swimming until relatively late in their development, so the juveniles will mostly use body-driven swimming, propelling themselves with vertical undulations of their elongated body and leaf-shaped tail fluke, while the adults will swim using their six flipper-like legs, keeping their clawed forelimbs folded up against the body to minimize drag. These ramphidonts, which we'll call gyrinotheres, will fill niches ranging from omnivorous generalists to small acanthivores to large predators that ambush terrestrial prey. There will also be an abundance of niches to be filled in the oceans. By this point, the tachypods and acanthopods will have begun to regain their former diversity and refill the empty seas. With so many pelagic niches vacant, the remipterids that were once restricted to the reefs and shallows will have the chance to spread into open waters. Most remipterids have 7 pairs of fins that are more or less equal in size and shape, that they flap in a rippling motion along the length of their bodies, a subcategory of median-paired fin swimming called rajiform locomotion, which provides decent maneuverability but is only efficient at slow speeds, and is therefore most effective for benthic or reef-dwelling species. But one pelagic clade may instead evolve to beat all their fins together, merging them into a single pointed wing-like surface, evolving what's called mobuliform locomotion, which is more efficient at high speeds and over long distances. This will allow these remipterids, which we'll call synopterids, to move into deeper waters and fill niches that were only occupied by body-driven swimmers before the mass extinction, feeding on plankton and smaller acanthopods in the open ocean. Meanwhile, some of the dorypods will evolve to replace the temnopods and other large predators. The dorypod's harpoon-like mouthparts evolved as a mechanism for spearing small prey without creating turbulence, but they can also be fired into the bodies of larger prey to inflict lethal damage, resulting in the evolution of a clade of powerful macropredators with torpedo-shaped bodies and thunniform swimming for speed and acceleration, a group that we'll call the xiphopods. But before these and many other acanthopod groups can achieve total dominion of the oceans, there'll be a window of opportunity for terrestrial clades to enter the sea and compete for pelagic niches. From the same ancestors as the hylotheres will come a clade of acrochirids which, like many of the gyrinotheres, will produce grubs that are adapted for aquatic life from the moment they're born, which will rid the adults of the need to return to the land to give birth, letting them lose any capacity for terrestrial locomotion and turn their limbs into powerful flippers. The majority of thrust will be generated from the front and middle pairs of flippers, while the hind flippers will be used for steering, and the dorsal and tail fins will resist rotational forces and keep the body stable. Their forelimbs will move forward and partially merge with the mouthparts to form a single streamlined feeding arrangement, their claws lined with rasping protuberances to latch onto fast, slippery prey. From these creatures will come the most successful radiation of marine ramphidonts, one that we'll call the Thrinaxorhynchids. Most Thrinaxorhynchids will be fast predators that chase down acanthopods and other nectin, but some will move into the niches of filter feeders, adapting the claws on their forelimbs into comb-like structures that spread open to engulf enormous quantities of plankton-filled water, while the spade-shaped mandibles press down to force water out of the oral cavity and strain out the plankton before pushing it into the throat. With the buoyancy of the water to support their bulk and the profusion of food in the surface waters, these creatures, which we'll call dictyorhynchids, will become the biggest animals on the planet, the largest species exceeding 30 meters in length. But as life in the oceans and on the supercontinent is replenished, there'll be many isolated and outlying areas that will follow a completely independent path to recovery. In particular, the island continent of Septentria will have remained in allopatric isolation from the supercontinent since before the mass extinction, and since it separated from the eastern continent before the interchange, the xenopsids and the ramphidonts, both having evolved on the western continent, will have never had the chance to colonize Septentria. So as its biota recovers, the Septentrian ecosystems will come to be completely unlike those anywhere else on the planet. The hibignathans will be some of Septentria's signature oddities, the Siniskian condition of fused limb girdles being utterly unlike any other living osteopod. But those few species that survive the mass extinction won't be sufficient to re-establish their former diversity and achieve dominance of the Septentrian ecosystems. Instead, other, more diverse groups will come from afar to claim the terrestrial niches for themselves. As always, the organisms with the best chance of making it to island habitats are flying animals, and as the only two clades to have evolved flight, the surviving Opisthophorans and Pleuropterans will furiously compete to regain control of the aerial niches after the extinction, rapidly radiating into thousands of new species to fill the skies. The Opisthophorans won't be able to grow as large as the Platypterans, but they'll still proliferate into innumerable clades of nectarovores, small predators, and scavengers, while from the Platypterans will evolve small frugivores, swift predators, and gigantic long-ranging species with wingspans of over 6 meters. And as part of this diversification, some members of both groups may end up losing their flight altogether. In Part 11, we discussed how flying animals tend to become flightless if they find themselves in an environment where there are no predators, as the high energetic demands of flight are no longer justifiable or necessary to maintain. This most commonly occurs when flying animals find their way to islands or other isolated habitats, but in the wake of a mass extinction, predators will become significantly rarer across the whole planet, providing the opportunity for mainland species to become flightless as well. Shortly after the end Cretaceous extinction, flightlessness independently evolved at least 6 times among various groups of ratites, as well as in other birds like the Dromornithids and the terror birds. Septentria will be an ideal place for flightlessness to evolve, as it will be devoid of the xenopsids and ramphidonts that come to dominate the mainland, giving flying species the opportunity to move into the vacant niches. The Septentrian Pipiodonts may give rise to one such flightless group, becoming small, forest-dwelling omnivores. Even without flight, their elastic gladius will let them jump many times their body length if they need to escape danger, and will give them a distinctive hopping or bounding gait as they move along the forest floor. Like many of the Pipiodonts of the new era, they'll live in social groups that keep in constant communication with each other. Along with the calls they produce with their stridulating teeth, many species may adapt their vestigial wings into frill-like display structures, used in attracting mates, intimidating rivals, and staying in contact with the rest of the group while foraging. However, flightlessness will only be a beneficial adaptation during the brief window of time in which the ground niches are largely vacant, and by the time the predators and competitors return, it will be too late to re-evolve flight, so many flightless groups end up going extinct soon after they first appear. But these flightless Pipiodonts, which we'll call Pterolophids, may be lucky enough to survive within the relative safety of the Septentrian forests. A similar transition is likely to occur in at least one clade of Septentrian Platypterans, the second and third pair of limbs that form the wing shrinking into a vestigial membrane between the front and back legs, making them resemble the now extinct Chlamypterans of Pyronesia. But while the Chlamypterans were constrained in their size by the limited resources of the tiny Pyronesian islands, Septentria will provide enough food and space to accommodate much larger animals, allowing these flightless Platypterans, which we'll call Dermatopods, to become some of the first megafauna to inhabit Septentria after the mass extinction. As mentioned in Part 11, giving up flight allows a species to adopt less efficient feeding behaviors like folivory, so one clade of dermatopods may evolve into large herbivores with long stilt-like legs and an extended cephalothorax to reach upward to comb through the trees. This group, which we'll call rhabdopods, will be Septentria's dominant megafaunal herbivores, and include both relatively small and gracile forest dwellers, as well as bigger, more robust forms that feed on stands of trees and open habitats. And with the evolution of large terrestrial prey will come a variety of predatory dermatopods that specialize in hunting them. One group will develop sickle-like claws on their front limbs to slash at their prey and wrestle it to the ground, and flexible limbs and backs that grant them the speed and agility to chase down their targets. Most species will hunt small prey like the Pterolophids and the smaller dermatopods, but a few species will be big enough to occasionally go after prey as large as the rhabdopods. This clade, which we'll dub Compsopods, will be the most successful predators to evolve on Septentria since the mass extinction. But although the dermatopods will be the first major group to repopulate Septentria's terrestrial ecosystems, it's only a matter of time before some unexpected competitors make themselves known. While Septentria and the supercontinent exist in allopatry, they're only separated by a narrow stretch of seaway less than 1,000 kilometers wide, which is more than close enough to allow species to raft from one landmass to the other. Not long after the extinction event, the mainland will see the evolution of a clade of ramphidonts that adapts for life above ground, with sharp claws on their feet to help them climb and scamper over rough terrain, and a pair of crest-like prominences on their mandibles, used both for display and to assist the forelimbs in unearthing prey from the leaf litter, for which will give them the name Coryphodonts. While most mainland species will remain fairly inconspicuous, at some point a few lucky individuals of one species will be washed out to sea on a mat of driftwood and arrive on the Septentrian shores. By this time, the dermatopods will already occupy many of the Septentrian niches, but recall that land area is the greatest predictor of which biota will have the competitive advantage, so the Coryphodonts, having evolved in the complex and highly competitive ecosystems of the supercontinent, will still be able to gain a foothold in the Septentrian ecosystems. As they diversify, one line of Septentrian Coryphodonts will move into the steppe and other open areas, where they'll be a lot more exposed to danger, so many species will invest in some form of defense. One clade will evolve splint-like plates of dermal armor along their back and cephalothorax, and many species may also evolve horns and spines to deter predators. Though many of these Coryphodonts may remain fairly small, the protection provided by their armor will give them the edge they need to evolve into heavy-set megafauna, serving as Septentria's dominant clade of grazers while the rhabdopods browse on the treetops. Alongside these armored forms, which we'll call fractiforms, a separate branch of Septentrian Coryphodonts may instead evade predators by clambering into the safety of the trees and hiding among dense vegetation. To ensure their claws stay sharp enough to be effective in climbing, their feet will evolve special joints and tendons that allow the claws to be retracted to stop them from wearing down when the animal visits ground level, an adaptation seen in many semi-arboreal animals on Earth, and one for which we'll call them Cryptonichids. One line of Cryptonichids will specialize for herbivory, gorging on the bounty of fruits, seeds, and leaves in the canopy, to the point that some species will eventually become too large to have their weight supported by tree branches. Although their claws will no longer be of any use in climbing, retracting them when not in use will still stop them from wearing down so they can remain long enough to be effective in hooking down vegetation. Though the rhabdopods will still be the dominant browsing herbivores across most of Septentria, these Cryptonichids, which we'll call Theristobrachids, will still be fairly widespread in forested regions, their feeding claws doubling as a means of defense. Some Cryptonichids may even evolve venom as a defensive measure. Since, by definition, venom needs to reach the bloodstream to take effect, venom glands very often evolve from salivary or other digestive glands within the mouth, so that the venom can be transferred when the animal bites the target and the teeth penetrate the skin. But there are more exotic possibilities, such as the venomous spurs on the hind legs of male platypuses, or the brachial glands on the upper arms of slow lorises that produce a venomous secretion that they then lick to mix with their saliva. In the case of these Cryptonichids, some of the scent glands on their forefeet may evolve to produce toxins that pass into the blood through the wounds inflicted by the claws. In time, these glands may become integrated into the claws, which will evolve grooves or hollow ducts to allow the venom to be delivered into the target. When the muscles in the foot contract to extend the claws, they'll simultaneously compress the gland to inject the venom, a similar mechanism to the fangs of selenoglyphous snakes. As the early members of this clade will mainly use their venom for defense, many species may develop aposematic coloration to advertise their dangerousness to predators, some species turning the prominences on their mandibles into colorful crests. We'll call this clade the Glyphonichids. But as they diversify, some Glyphonichids may also use their venom to take down large prey, letting them compete with the compsopods for the niches of Septentria's dominant predators. In one group, the forelimbs will undergo centaurism so that their fang-like claws will be better positioned for seizing prey and injecting the venom. As they get larger, they can rely more on size and strength to take down prey, so their venom will likely be less potent than the smaller forms, even being completely absent in some species. Without any xenopsids on Septentria, these large glyphonichids, which we'll call archonichids, will fill similar niches to those occupied by the anaxathias and xerodonts on the mainland, becoming some of the largest of all predatory ramphidonts. And so dawns a new golden age for life on this planet. If we wanted to, we could keep on fleshing out the history of the biosphere period after period until the planet is rendered uninhabitable by the expansion of its sun. But for our purposes, this is as good a place as any to leave things off, and to declare this particular time period as the present day. And now that we've finally reached this point, it's about time we gave this planet a name. In keeping with standard astronomical naming conventions, let's give it the official designation of Tira 292b. However, along with a menagerie of forms that appears after the mass extinction, the new era will see the emergence of one particular adaptation, one with the potential to shape the future of the entire biosphere. Next time, in the final episode, we discuss the evolution of sapient life. Thanks to all the artists on Discord who contributed artwork for this episode. If you didn't notice...
Talk about that announcement for a minute. The announcement is my channel called Terraforma, and what the Terraforma and the Hollow World Building. If you want to check it out, it's close. It's kinda like it, the Alien Biosphere series. Today we are drawing the anatomy. You can watch that in here. So that's the announcement. So, bye guys, and see you on the next episode, which is most likely the 4 episodes of Battle Arenas, because we don't need an extra episode this time. Yes. Oh, bye guys.